different. The difference between what bosons and fermions are. I have, well, I guess I'll go according to my notes here. I'll follow my notes. I have spin first, and then bosons and fermions. So let's talk about half spin. The spin of the electron, or the spin of the proton, which happens to be half spin, which means that the spin or the angular momentum of an electron at rest, it has no orbital angular momentum, it has no r cross p, all it has is spin. So spin is a kind of angular momentum that's attached to a particle. It's your choice whether you want to think of it as just an abstract concept or whether you want to think of it as a tiny little thing which is literally spinning about an axis. And when I say it has no momentum, I mean to say it has no center of mass momentum. And it's a matter of choice and taste whether you want to think of it as literally being a little spin or just an abstract property that you, mathematical property that you attach to the electron. But whatever it is angular. To the discovery of spin and the fermionic character of electrons, basically. The fermionic character implies two things, and they're actually believed to be related to each other, but they're different. One of them has to do with the spin of the electron. Spin of the electron is half spin, and that means that the spin, as far as the spin goes, if we forget about the orbital motion of the electron and so forth, the electron has two spin states corresponding to spin a half, plus a half and minus a half. The other property that qualifies the electron as a fermion is that it satisfies the Pauli exclusion principle. You can't put more than two of them into the same state. In talking about the states, spin counts. So if, for example, we ignored the spin, and, for example, we talked about putting two electrons into the ground state wave function of a hydrogen atom, yes, you can do that. You can put two electrons into the lowest energy level, but only because you have the spin to soak up the Pauli exclusion principle. And so you put them in with opposite spin. If you try to put a third one in, you can't put it into the ground state. If you try to put a third one in, let's say because we're dealing with lithium, plus for helium, we can put both electrons into the ground state. In the approximation that we ignore the interaction between the electrons. In other words, in the chemist's bad approximation, incidentally, these days chemists are very sophisticated quantum physicists, really good chemists, and they're very sophisticated. But, you know, the old picture of the atom, the shell model, and all those sorts of things that were simplistic, which didn't work very well, but, you know, they work a little bit. You can put two electrons into the ground state of the helium atom, so the helium atom behaves as if you had two electrons both in the lowest energy state, and that's okay because they have opposite spins. If one is up, then the other is down. If one is down, the other is up. In fact, those two electrons are entangled. They're entangled in exactly the way that, well, they're entangled. One is up, the other is down, one is down, the other is up. And that's an entangled state. Once you go to lithium, you can't put another electron into the ground state. And I don't mean into the ground state of the hydrogen, of the helium atom. I mean, of course, into the ground state of the electron wave functions in the vicinity of the lithium nucleus. The lithium nucleus also has a collector, a charge, and it also has a collection of wave functions for electrons. You can put the first one into the ground state, you can put the second one into the ground state, but then the third one has to go into another state. Simply no room for it. By room, I mean from the point of view of the exclusion principle. So, you start filling another shell. And how many energy levels are there at the next shell? Well, we can draw our energy level picture that we drew before. Angular momentum 0, which is called the S wave, at least for the simple approximation in which the electrons don't interact. There's the ground state, and then there are excited states which still have angular momentum 0, and so forth and so on. And then there's the P waves. The P waves are angular momentum 1, or orbital angular momentum 1. P stands for something I don't know what. And the first P wave has more energy than the first S wave, and it has 3 states. The 3 possible states of orbital angular momentum 1. And then there are above that, and by the accidents, or they're not really accidents, of course, but by the funny mathematics of Coulomb potential, the first, there's degeneracies, extra degeneracies that I've indicated here on the diagram, and so forth and so on. SPB, that's spectroscopic notation. At the next level, at the next angular momentum, this is L equals 0, L equals 1, L equals 2. At the next, at the B wave level, L equals 2, the lowest energy state is already up to here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, so forth, 5 states for L equals 2. And that's what the pattern of energy levels looks like. Okay, so you go to the lithium atom. In the lithium atom, you put in 2 electrons into the lowest energy state. So they're both in the lowest energy S wave state. And now you have an extra electron you have to do something with. Well, you could put the extra electron upstairs at some higher energy state, but it would be unstable because it would decay by emission of a photon, which we haven't gotten to, but it would decay down to something of lower energy. What you can do is put the next electron into any one of these 4 states. Okay? Keep going. What comes after lithium? I can't remember. Beryllium. Okay, then you come to beryllium. Beryllium, you fill the lowest one, and you fill one of the next levels. But wait a minute, there's 4 electrons now, so you fill 2 of them.